So we know the equation of the tangent line, L of x, is always given by f prime of a times x minus a plus f of a. That's our standard equation of the tangent line. So if we want to know the change in L, the change in L is L of a plus delta x minus L of a, which is equal to, so I'm going to put a plus delta x in right there. So this would be f prime of a times a plus delta x minus a plus f of a. So that's just this expression here, and then minus LA, so minus f prime of a times a minus f of a. This expression is 0, and this will cancel out with that. So my change in L is simply, and notice here that that a and that a will cancel, so my change in L is f prime of a delta x. So that's what my f prime of a is. Now, if I look at the change in y for the function, so we know that f prime of a is the standard part of the change in y over change in x. Right? So we know this. This is our definition of the derivative. So I want to get a handle on this change in y then. Can I relate this back to the derivative? Well, if f prime of a is the standard part of this, that means they're infinitesimally close. So that means f prime of a is infinitely close to change in y in change in x. But what does it mean to be infinitely close? It means that their difference is an infinitesimal. So that means that f prime of a is equal to delta y over delta x plus some infinitesimal epsilon. I don't know what the infinitesimal is, but for this all to be true, for the derivative to be the standard part, means the derivative is infinitely close to delta y over delta x, which means that the derivative must be delta y over x plus some infinitesimal. So solving for delta y in here, I multiply by delta x, so I get that f prime of a delta x minus epsilon delta x is equal to delta y. And this leads us to a very important observation, that this right here, f prime of a delta x, was exactly what we found to be the change in y, f prime delta x. And so we see here that the change in y is equal to the change in our tangent line minus some infinitesimal change in x. And this observation gives rise to the next theorem. So let me clear our screen and place the increment theorem straight from the book, which says that if y is a function and f prime exists at a certain point and delta x is an infinitesimal, then the change in y, delta y, is also an infinitesimal, and further yet, delta y is equal to f prime of x delta x plus epsilon delta x for some infinitesimal x, or infinitesimal epsilon, which depends on x and delta x. And recall we worked out that this value here is the change in our tangent line. And so we're going to create or define a new function related to this called the differential. Now, the differential is composed of two variables. We have first and foremost that the differential here of x is our independent variable. And so dx will typically be set equal to our change in x. Now, technically, it's free to be anything it wants to be because it's independent. But again, in our context, we'll almost always make it to be equal to our infinitesimal change delta x. Now, on the other hand, our differential of y is a dependent variable, and it is defined in this way. So if y equals f of x, then dy equals f prime dx, which we could change that because we know dx equals delta x. So in general, we could say that this is equal to f prime d delta x. So that's what our, at least when we're talking about derivatives, our differential of y will always be f prime dx. And again, because dx is associated with the infinitesimal change in x, we could think of dy, the differential of y, as being f prime delta x. And this gives rise to some nice notation, and something I haven't stressed before is different origins of these notations. So on the left-hand side here is what's called the called Leibniz notation. So after the mathematician Leibniz, so this is Leibniz notation. And on this side, with the prime, is the notation that was introduced by Newton. And so we have two different forms of writing the derivative, Newtonian notation and Leibniz notation. They mean the same thing. They're both related to the derivative. And the differential, this incremental or infinitesimal change in y divided by the infinitesimal change in x, is exactly what we're talking about when we write f prime. So they're equal in terms of notation. I will more often than not use Leibniz notation, but in times I'll use Newtonian notation. Just depends on what is most convenient. So let's take a look at this. So we've got differentials now. We have the increment theorem. So I want to just run through an example in which we compute the differentials, we compute the delta y, and we go through and find the epsilon that makes the increment theorem valid.